Hello everyone, this is a video summary of our paper, Noisy Recurrent Neural Networks, that will appear in NeurIPS this year. The main goal of this paper is to introduce a stochastic version of recurrent neural networks, RNN. At a high level, RNNs are networks of neurons with feedback connections, specially designed to deal with sequential data. They can use their hidden states to process variable length sequences of inputs. It has been shown that they are universal approximators of dynamical systems. At the level of schematic, the networks take at each time step an input X, feed it to a hidden state of the network H, which then produces an output Y. The network itself can be unrolled in the following fashion. We consider a supervised learning framework for these networks. The data consists of pairs of inputs and targets, where the inputs are sequences and the targets are class label in the case of classification. The models are described by the following parametric non-autonomous discrete time dynamical systems. So in these two equations, H is the hidden state of a network, and Y is the output variable. A is typically a nonlinear activation function, and G is an output function. To give you an idea of this model, the simplest example is a so-called vanilla model, where the activation function A is taken to be a hyperbolic tangent function, and G is a linear function in the hidden state. Data here collects all the learnable parameters. To do learning, we need to specify a loss functions. And we are going to minimize these loss functions using empirical risk minimization. So how can one design a stochastic version of RNNs from this setup? There are two steps. First, we add leaky integrator, and then we inject noise into the hidden states of the network. Typically, we use Gaussian white noise. It turns out that this outer equation can be interpreted as certain discretization of a continuous time stochastic differential equations that looks like this. Inspired by this observation, we consider the following SDE model for RNN. This model is described by a general class of SDEs. So in equation 6, we can see that the SDE is specified in terms of the drift F and the diffusion coefficients sigma. Intuitively, we can think of this equation as a noisy perturbations of the corresponding deterministic system, since we add the diffusion term into the otherwise ordinary differential equation. And to be able to do analysis with this equation, we assume uniformistic drift and diffusion coefficients, and also boundedness of these coefficients. There are various benefits of this continuous time formulation. First, from the point of view of design, sampling from these RNNs give us discrete time RNNs. This provides us guided principle and flexibility in designing new architectures. Second, from modeling point of view, in situations where the input data are generated by continuous time dynamical systems, it's desirable to consider learning models which are also continuous in time. Lastly, from the analysis point of view, it turns out that we can borrow a rich set of tools and techniques from the continuous time theory to study these systems. Now, there are some choices that we need to make when it comes to choosing the drift and the diffusion coefficients in the SDE. For our case, we choose a drift term to be a sum of a linear component and a Lipschitz nonlinearity. As for the diffusion term, we choose it to be sum of an additive and multiplicative noise. So here epsilon is a small parameter, Sigma 1 and sigma 2 are the noise level corresponding to the additive and multiplicative noise. By setting epsilon equals 0 at inference time, we can view noise injections in these networks as a stochastic learning strategy. Now, there's also a choice that we need to make when we discretize the SDE. We consider explicit Euler-Maruyama integrators, which we can think of as a stochastic analog of Euler-type integration scheme for ordinary differential equations. This results in the outer equations in 9, and we are going to call this discrete-type noisy recurrent neural networks. So here are our main results. From theoretical point of view, we study noisy RNNs via the lens of implicit regularization. In particular, we derive explicit regularizer induced by the noise injections through a perturbation analysis in the small noise regime. It turns out that this regularizer reduces the state-to-state Jacobians and Hessian of the loss function according to the noise level, thereby promoting flatter minima and biasing towards models with more stable dynamics. As we can see from these Hessian plots, the loss landscape for the noisy models is indeed smoother than the one from the deterministic model. Moreover, we show that in this small noise regime, noisy RNN promote classifiers with large classification margin. This is an attribute which has been linked to improve model robustness. We also provide sufficient conditions for stability of the SDE, showing that noise injections can indeed improve stability during training. On the experimental side, we demonstrate that on benchmark datasets, the noisy RNN classifiers are more robust to various types of data perturbations when compared to other recurrent models, while retaining state-of-the-art performance on clean data. For example, this table shows that noisy RNNs are more robust with respect to white noise and salt and purple data perturbations on the order MNIST task. And the same story are told by these two plots here. As we vary the amount of noise that we inject into the data, noisy RNN is more robust when compared to other recurrent models. To summarize, noise injection can be viewed as a stochastic learning strategy used to improve robustness of learning models against data perturbations. Here, within the framework of SDEs, we study RNNs trained by injecting noise into the hidden states and the implicit regularization effects of these noise injection schemes. In particular, we show that noise injections can promote classifiers with large classification margin. Our experimental results are in agreement with the theory and its implications, and we find that these classifiers achieve superior robustness to input perturbations. For more details, we invite you to check out our paper and code. Thank you.